Welcome back to Python. Today we're going to be continuing on with our blockchain series. Alright, so if you remember in part 1 of our series, we covered the basics of how blockchain works and the different types of blockchain networks that exist out there in the world. Today we're going to dive more into the blockchain cryptography and what actually these hashing functions are doing. So just going a little bit deeper into the structure, we're going to talk about some applications, and then we're going to talk about what the future of blockchain may hold for us. So let's get started talking about cryptography. So if you remember the other day when we were talking, we talked about the fact that blockchain is based on a hash data structure. And so when we build blockchains, we're using cryptographic hash functions to build that distributed ledger technology, to build the blockchain. Now, what's unique about these hashing functions is that they create secure and unique digital signatures for transactions in a blockchain network. But this doesn't have to be scary. All a cryptographic hash function is a mathematical function that basically takes some input data and then generates a fixed sized output. And that output is what we know as a hash. And each of these hashes has some unique properties to them that we should all know about. The first is that hash functions are deterministic. So anytime you provide the same piece of input data, you're always going to generate the exact same hash. Another property of hashing functions is that they're quick and efficient. So you can generate a hash almost instantaneously, and the size of the input data doesn't matter. We're basically just encoding and decoding data between users. Another unique property of hashing functions is that they are one way. So it is literally almost impossible to figure out how to decode a hashing function without having the input data or the proper key to decode that data. And then lastly, because of the other properties of a hash function, they are basically collision resistant. So it is extremely difficult to find two different input datas that generate the same hash. And that is because of the extremely unique nature of hash functions. So these properties make hash functions ideal for blockchain networks where we're looking for high-level security and immutability. So these hash functions are what make our blockchain networks so secure. So now we're going to look at some basic code again to build some of these hashing structures. So if you remember from the other day, we were using a library called hashlib. First off, we're going to start by importing hashlib. The next thing we're going to do is create a hash object, and we are specifically going to be using the SHA-256 algorithm. So all we do to create this hash object is create a new object called hash object that will be equal to the hashlib library.sha256. So in this first step, we basically initialize that hash object. After we've initialized that hash object, we can come in here and add some input data. So we're going to come in and say hash object.update, and then we're going to tell it what data we want to produce. So in this case, I said, give me the B, which is the bit or the byte code, and I want you to produce this or convert this input data into a hash function. And so I said, hello world, my name is Paul. Now that we've updated our object, we're actually going to generate the hash of that object. So we're going to create a new object that's called hash value, and hash value will be equal to the hash object, and then we're going to say hex.digest that hash object. And then lastly, we'll just print it out. So let's go ahead and print this. And you see that immediately we get this turnaround, and hello world, my name is Paul has been turned into this long string of numbers and lowercase letters. Now, if I went in there and changed the data for the hash object, and let's say I removed my name is Paul, and we just had hello world, when we run this, we're going to end up with a different hash value. So let's compare. So in the last one, we had B47290 as the last 6 digits of our hash value. Now let's run it and see what we get. And you'll see now we have 94EDD3. So for every unique input vector or input string that you provide to this algorithm, it will give you a unique hash function as the output, or hash value as the output. And that is what makes the cryptography behind blockchain networks so unique, and what really increases the level of security for blockchain networks. Now, if we were working with a publicly accessible or open source decentralized blockchain network like Ethereum or Bitcoin, one of the things that you have to do when you try to send money to someone on the network is have your transaction verified. And that's typically done through a consensus algorithm like proof of work or proof of stake. So when you use a proof of work algorithm, what happens is your data and your public and private keys are sent to a node. That node does the complex mathematics to solve the work for your transaction, and then the data for that transaction is then verified, added to the block, and then your money is sent. And so verification of your data is another important step when we are dealing with blockchain networks. And this is something that we talked about the other day, and this code should look very familiar. We're going to use our knowledge of hash functions to verify some data and verify some blocks on a blockchain, and then spit out our output values. So we're going to start again just by importing our hashlib. Then we're going to create the class block, and block consists of the init, so the data about that class itself. And then we're going to create a function to generate the hash based off of the data, the previous hash, and then that SHA-256 algorithm. And that block hash will then be returned from the generate hash function. Now, outside of there, we have the blockchain class. The blockchain class consists of the init for the blockchain itself, a create genesis block class, an add block class, and the is valid class. And we covered all this in our first day of this tutorial. That's why I'm moving kind of quick on this information. If you have not heard that lesson yet, go back and watch part 1 of this series. And then after we've defined our classes, we can go in there and initialize our blockchain by saying my_block, so creating that object, equals the blockchain. And then on that blockchain, we're going to add some data. So we're going to say my blockchain, add the block 1, add block 2, add block 3. Now, once we've added the data to our blockchain, we can check to see if the blockchain is valid by using the isValid function. And then we can also print out all of the data for the blockchain by saying for block in my blockchain.chain. So we'll go ahead and run this. And what we get is an output of all of our different blocks, including our Genesis block, and then a validation that our block is verified and it is correct. Excuse me, that our blockchain is correct. And so you see down here we have true. So that's the basics of what we covered in the last tutorial, and that's the basics of how hash functions allow us to verify data on a blockchain network. Now, as I said previously, when you're sending money on a network like Ethereum or Bitcoin, you actually have to have your transactions signed and verified before any money is sent. So verification and signing of transactions is a major part of the security that makes blockchain so immutable and impermeable to change. Okay, and we do this by having public and private keys. Now, if you're not familiar with the concept of a public and a private key, think of a public key like your username. So when you're on Facebook or Instagram, you have a name that you show to the world, that you show up in the database as. That would be like your public key. That's how someone can identify you. That's how they could find your profile. Now, your private key would be something like your password. Your password is your own information. It's something that you want to keep to yourself to ensure that your account remains secure. If you lose your private key and someone else gains access to your account, they technically could steal all of your money. And so on a network like Bitcoin or Ethereum, these public and private keys are how we can verify transactions between individuals. Okay, so for example, your public key may be passed to a node for that node to then verify the transaction that you want to occur between you and another person on the network. And that's going to take your public key, verify the amount of money and the transaction that you're asking to use or to do. And then it's going to send that data, once it has been verified, to the public key of the recipient. And through that verification process, your private key is used to ensure that that data that you're asking to send is actually being asked to be sent from your wallet. So you're not trying to steal money from someone else. And so each of these is a unique identifier to your account specifically. And as I said, the public key is publicly visible. The private key is a secret code that you want to keep to yourself. So we're going to practice generating these keys here real quick. And to do this, we're going to use a package that's called ECDSA. And ECDSA is a specific algorithm. It's the elliptical curve digital signature algorithm. To put it very simply, it's a way of encoding and creating secret keys to pass back and forth between machines on the same network. So there are other versions of this, like for example, if you use SSH secure shell layer or VPNs, they use some form of one of these digital signature algorithms to create that connection between your machines and ensure the security of your connection. So we're going to go ahead and install ECDSA by going pip install ECDSA. Then we're going to import ECDSA, and then to actually create our values, we start by generating a private key. So to generate a private key, we're going to create a new object called private key, and private key will be equal to that algorithm dot signing key, and signing key is a built-in sub package of ECDSA. So you just go ECDSA.signing key, and then you tell it what kind of curve you want to be used to generate your specific private key. In our case, since we're typically using the SHA 256 algorithm, we're going to use a 256-bit key also. So we generate that private key first, and then from the private key, you derive your public key. So we're going to create a new object called public key, and public key is equal to the private key dot get the verifying key. So this is built into the ECDSA package, and this function takes your private key, converts it to a publicly visible public key for you to use on that network. And then we can simply just ask for these two values to be printed out. And then when we actually run these functions, you can see our private key here as well as our public key. Now notice that the public key is significantly longer than the private key. And on a network like Bitcoin or Ethereum, from my understanding, typically your public key is used as the beginning identifier of your transaction. So your data that is stored on the blockchain, your public key is part of the data that is encoded on each block. So on each individual block for that transaction that you have sent to someone, your public key is there, the data for that transaction is there, and then any other information that Bitcoin may want to store for each transaction, like the time, the previous hash, whatever else is there. Now, one important thing to remember here is that just because this key is openly accessible to the network does not mean that someone can hack your account. Again, remember that each specific input value in this kind of cryptographic signature is unique. So they would have to have your private key or some other piece of information to reverse engineer your private key and your data from your public key. It would be very, very challenging, and as far as I know, it has not been done yet. So that's the basics of actually generating these keys. Now what we're going to do is use those keys to sign transactions. And so this is the point where we combined the ECDSA library and the hashlib library. So we're going to import both of those. We're then going to generate our private key just as we did above, and then we're going to generate our public key as we did above. Next, we're going to create a transaction. So we're going to create a new object that's called transaction. We're going to label the sender in there as Alice. We're going to label our recipient as Bob, and we're going to ask to send 10 Bitcoin or 10 coins, however you want to think of it. Now, once we've created that transaction that we'd like to be signed, we're going to take that transaction and convert it to bytes. Okay, so we're going to take that transaction, convert it to a string, and then we're going to say encode this using the UTF-8 algorithm or structure and call that our message. Now with that message, we are going to convert that message into a hash function using the SHA 256 algorithm. So we're going to say hashlib.sha256 of that message .digest, and that will equal the hash object. Now, once we've created our hash object, we're ready to sign that object. We're ready to put our signature or our stamp on that data. So then we create a new object that's called signature, and signature will be equal to the private key dot sign and the piece of data that we're interested in signing. Now, once we've signed the data, we can come in here and use our public key, and we can say assert this data using my public key .verify, which is a built-in function, and then you tell it where your signature is located and what data it is transporting. And then after that, we can just give ourselves a little message to say that we've done a good job and our data was successfully transferred. So we'll go ahead and run that. We have now created a transaction, calculated or computed and generated our keys, signed our data and our message with our private keys, sent that to whatever blockchain we're interested in, and we have successfully interacted with a blockchain network. Now we're going to move on and start to talk about some real-world applications of blockchain. So the first thing we're going to do today is create a cryptocurrency. And if you are unfamiliar with the concept of cryptocurrency, this is what I've been talking about, Bitcoins and Ethereum. These cryptocurrencies are basically just digital assets. So they're a way of basically exchanging value between individuals. And so we are actually going to create and design and implement our own cryptocurrency. If you were actually in my class, you know that during our lecture, we talked about a cryptocurrency that had 3 classes built into it: the block, the blockchain, and then also a transaction class. And I moved away from that. It was more complicated than we needed. If we wanted to continue to have the transaction class in our cryptocurrency here, we would have also had to add a user interface basically, or user profiles to store all the other information. So I had successfully created the cryptocurrency, but added too much abstraction in it, and it was overly complex for our needs. So I've switched to a different example, and parts of this example come from my own work, and then I also have included a reference here from Free Code Camp of how to create a cryptocurrency using Python. So in this implementation, we're actually just using the same 2 classes that we've been working with for the last 2 parts, for both parts of this series. So we're going to have the block class again, and then we're also going to have the blockchain class. This time you need to have 4 imports. We're going to import hashlib, we're going to import JSON, import time, and then date time also. In our block class this time, not too much is changing. We still have an index, we've got a timestamp, we've got data that we want to transport across the network, and then we need to know the previous hash of the last block. Now, the one thing we did have to add here is in this implementation, we're going to be using a consensus algorithm. So we'll be using proof of work here. So we need to know the proof number to be able to appropriately verify and sign these different transactions. So in our init function, we're going to have index, proof of work is equal to proof of work, timestamp equals timestamp, data equals data, previous hash equals previous hash, and then the current hash will equal self.calculate hash. And our calculate hash function is very, very similar to what we've already been using. We're going to change the format of our data a little bit though, just so we get a pretty output. So this is essentially going to provide us with a text-rich output, and that's what this rep R does right here. Is this is specifically asking for an information-rich output for our data here. So in the calculate hash function, nothing changed except the format of the data. You can see we're still just passing the index, the proof number, previous hash, data, and the timestamp. And then we ask for it to return the hashlib library and the SHH-256. We ask it to encode our data, then digest that, and return that value to us. And then again, this last part right here, define double underscore rep R double underscore, is specifying that we want a very information rich output for our format. So we just get more data basically. And that's it for the block class. The block class is fairly simple, and it's our base object on our blockchain here. Next, we're going to actually define the blockchain itself. So again, the blockchain, the init, is very similar to what we've worked with before. We start by defining the chain itself. The chain in this case is just going to be an empty list. Then we're going to define the current data. Again, current data at the beginning is just empty. We create a genesis block. That's our starting block, typically at index 0. And then we're going to specify the nodes here, or we're going to set our nodes because the nodes are where our proof of work algorithm is going to be taking place. Now, after we've defined our init, we're going to create our genesis block. Create genesis block just consists of construct block. And in order to be able to construct that block, we need to know the proof number. Because we're starting with a Genesis block here, the proof number of the Genesis block is 0, and the previous hash of the Genesis block is also 0. So that's it for Genesis block. Then we need to be able to get the latest block, and the latest is basically just a function that is going to ask for the blockchain to return self.chain -1. So from the current position, go backwards 1 in time, and that was your latest block that you worked on, and then from there it can work forward in time. Now, as you saw in the create Genesis block, we're actually calling on a function in the blockchain called construct block. And construct block is right here under get latest block. Construct block takes 3 parameters: self, proof number, and previous hash. And we ask it to construct an object that's called block. Block just consists of a block. And the block here needs to have an index, a timestamp, a proof number, previous hash, and some data. And each of those is defined up here in the block class. So all we're doing is using the block class itself, the init of the block class, or the init function of the block class, to build a block. And then once we've built that basic structure of the block, we say access the current data, and then take that data and chain append the block. So add the block that we just constructed to the existing blockchain, and then we ask it to return that block. And so that is the very simple process that we use to construct a block in this example. Now, obviously, since we're building a blockchain and we have a bunch of different blocks, we need to be able to verify or validate that each of those blocks is correct. So next, we're going to call on a static method. And that static method will be check validity, or check that a block is valid. Now, to check that the block is valid, we need to know the current block as well as the previous block. And we simply say that if the previous block index +1 does not equal to the current block index, so the position of the last block plus the value 1, so moving forward in time by 1 position, if that does not equal the current block's index, then I want you to return false, as in it is not valid. And then we say elif the previous block calculated hash does not equal the current block's previous hash, we want to return false. And then we also say that if the blockchain verifying proof and that block proof number on our current block does not match the previous block's proof number, we have to return false, because that would mean that somewhere our data got mixed up. And then the last one is that if our timestamp on the current block is not less than or equal to the timestamp on the previous block, that we need to return false. The reason for that is a block that is currently being worked on is obviously occurring later on the blockchain than the previous block would have. So the timestamp of the current block should be in the future in comparison to the previous block. So it should have occurred more recently than the previous block. And then lastly, of course, if all of those others are not true, or are not false, then we want to return true. So we want to say, yes, this is a valid blockchain at this point in time. Now, after we've checked our validity, we also need to be able to add new data to the blockchain. So we're going to create an item that's called new data. New data needs to have a couple of different parameters here. We need to know who the sender is. We need to know who the recipient's supposed to be. And then we also need to know what quantity of money or currency that they want to send across the network. And so to do this, what we're going to do is take our current data object that we created up above, that empty list, and we're going to append some values to that current data object. So we're going to append sender, recipient, and quantity. And notice that even though current data is a list, we are actually inputting this data as a dictionary. So we're taking the dictionary and then converting it to a list in the current data object. Now, once we've got all of our data taken care of and our validity algorithm or function taken care of, we can come in here and actually start to think about the mining process and the consensus process of how do we want to handle the signing and the verification of this data. And so we're going to start with the proof of work algorithm here, and this will be a static method. So we're going to say at static method define proof of work, and it will require the last proof. And for our proof of work algorithm here, it's really not that complicated. Now remember, we are working with a small cryptocurrency that we're creating out of thin air here. So we're working with an example, not necessarily 100% a real world situation. As I said, I was working with a more complex situation earlier, and I reverted back to this example. Anyways, though, for our proof of work algorithm, we simply are going to set the proof number initially to 0. So we're creating an iteration variable. After we've created that iteration variable, we're going to say while the blockchain dot verifying proof, which will be another function later on in our class here, we're going to ask for the proof number and the last proof. And we're going to say if this proof number and the last proof is false, then we want to take the proof number and add 1 to the proof number. So we want to iterate over this variable. And then after, when that condition is no longer true, we want to return the proof number. And that's as simple as it's going to be for this example. Obviously, in a real world situation like Ethereum, Bitcoin, Dogecoin, whatever you're working with, the proof of work algorithm is much more complex. It is very complex calculus and mathematics that has to be done by a computer. No one's doing that by hand. And that's why we talk about Bitcoin mining and mining facilities. All of those are just servers that are doing proof of work or proof of stake consensus algorithms and verifying transactions to make money. Now, one of the things that we haven't talked about so far is the mining process. So in our blockchain network here and for our cryptocurrency, we are going to define a function that's called mine the block. And mine block basically just requires the miner's details. So what we're going to say is that to begin mining a block, there has to be new data. So we're going to say self.newData. We specify a sender. We specify the receiver, who will be which will be the details of the miner, the person that's mining the data. And then we specify the quantity that they should receive for proving or verifying a transaction. And in our case, I set that value equal to 10. Now, after we've defined that new data for the miner, we're going to call on ourselves here and say the latest block, which is one of those functions we created up above. And we're going to say the latest block is equal to the last block, an object called the last block. And then we're going to say that the last block dot proof number is an object called the last proof number. So we're basically just gathering the variables that we need to actually do our calculations here. And then lastly, you see we're creating another object that's called last hash, and that'll be equal to the last block dot calculate hash, that function from up above. Now with this information, we're going to use that information and we're going to say construct a block based off of this proof number and the last hash number, and that will be equal to the block. And then we're going to ask it to return the value pair mapping of that block. So basically just return our data after you've computed and constructed that block. Now, in order to be able to mine a block, somebody has to be able to access a node. So we have built into here a node function called create node. Create node just needs to know the address of that node. So what machine is this going on to? And then we simply say that self.nodes, because we instantiated or initialized a node up above, and we're going to say dot add that address and then return the value of true to us. And then our second to last function here is another static method that obtains the block object. So it's basically returning the block data to us in a different format. So this is just the information that we created or we accessed up above and returning it as a different type of object. And then our last function is the verifying proof function. And the verifying proof function requires two inputs, the last proof and the proof. And then we're going to say that we want to create an object called the guess, and the guess will be equal to a function that is the last proof and the proof. And we want to encode that data. And then we want to generate a hash value for that data. So we say hashlib.sha256 of guess.hex digest is our guess hash, and then we want to turn that guess hash. This specifically is only for this example. We could actually remove these values here and the function would work exactly the same. Now what we're going to do is come down here and actually start to work with our blockchain. So we're going to start very similar to how we did in a couple of our other examples. We're going to start by just creating our new blockchain. So blockchain object will be equal to the blockchain class. And to that blockchain class, what we're going to do is figure out what our last block was. And that'll be an object called our last block. And then what we're going to do from there is print that last block just to make sure it prints out correctly. And then we're going to figure out what our last proof number was by taking that last block dot proof number and save that as a new object. And then we're going to calculate our current proof number by taking the blockchain class dot proof of work. So taking our proof of work consensus algorithm and then using the last proof number parameter, passing that to the proof of work algorithm. Next, we're going to add some new data. So we're going to say blockchain.newData. We're going to specify our sender. We're going to specify our recipient and then the quantity of money that we're sending. So in this case, we're going to send one currency across the network, or we're going to exchange one piece of currency across the network. After we've created our new data, we can come in here and figure out what the last hash number was. Once we have the last hash number, we can construct that block from the proof number and the last number. And then these last two lines are just going to tell us that our currency was successfully mined, and it's going to print out the blockchain for us. So let's go ahead and run that. We successfully mined our cryptocurrency here, and you can see all the different values that were sent. You can see that it's got our data saved right here and each of the timestamps for our interactions or for our transaction. So that's one of the main applications of a blockchain network right now. And what you just saw is a very simple implementation of a cryptocurrency. But this is where things like Ethereum and Bitcoin and Dogecoin started. They started as these concepts, and then from those simple concepts, they turned into networks with millions of users that are publicly listed on the stock exchange for people to purchase. Now, one of the other possible applications of these blockchain networks is using them for smart contracts. And smart contracts can be almost anything. Like an NFT, a non-fungible token, is technically a smart contract. Any kind of financial documents that you have, like a loan, that can be translated into a smart contract. The deed to your house, that could be translated to a smart contract. Your health insurance plan, that is a contract that can be converted and hosted on a blockchain network. So any of these things that you use and experience in your everyday life can be placed on one of these decentralized blockchain networks. And so what we're going to do now is practice developing a smart contract using Ethereum. Now, one caveat to this example is the fact that I'm working from the Google Colab environment. So I'm on a virtual machine right now. And because I'm on a virtual machine, I had a couple problems while I was developing this, primarily related to dependencies. If you are working on your own local machine, you likely will not have any of the problems that I experience. So if you're reading through this code, some of it might look weird to you. Now, because I started to have some of those issues, we are actually going to start by setting up a virtual environment here to ensure we can get all the correct packages and dependencies that we need for this code. So we're going to start by saying pip install virtual environment. Once you have your virtual environment downloaded, you can say python 3-m virtual environment, and then this last part is where you name your environment. So I just called it my environment. After we've got our virtual environment created, we say source my environment /bin/activate, and this line of code will change depending on whether you're a Windows, Mac or Linux user. Now that we are actually in our environment, we can start to download the packages we need to interact with Ethereum. And if you remember from our last tutorial, I told you that Ethereum and all of these blockchain networks are migrating us from Web 2.0 into Web 3.0. So Web 3.0 has a totally different set of web protocols than Web 2.0 does. So we need a couple of different packages here to be able to interact with the Ethereum network. The first of which is protobuf. Now, this is one of those issues that I was having working from the Colab environment. Protobuf has to do with the metadata of the contracts that we will be sending across the network. And so if you are working from the Colab environment and you try to download protobuf without being in a virtual environment, protobuf will interact with the TensorFlow metadata subpackage and not let you actually create your contract. So it's very important that you set up and activate your virtual environment before you start to download these packages. So the first line of code here is going to be pip install protobuf, and I specifically asked for a version that is greater than or equal to 4.22, and that was because of that issue I was dealing with TensorFlow. Next, we need to install pi-sulk-x, and sulk is standing for Solidity compilation or Solidity compile. Solidity is the object-oriented programming language that Ethereum and other kinds of blockchain networks use to handle smart contracts. So Solidity is specifically designed for this application. And so those are the two packages we're going to start with. When we get down to our code here, the first two things we need to do are import sulk-x specifically, and then we also need to say from sulk-x import compile standard. Compile standard is our standard compiling code, our standard compiling function for Ethereum and for Solidity. After that, we have to specifically install sulk because there is a difference between sulk-x and sulk. Sulk is the package that's actually capable of compiling our data. Sulk-x is the updated version. So the original compile function is built into sulk, not sulk-x. After we've specified and installed sulk, we can come in here and start to lay out our contract. And our contract for this example is going to be very simple. We're going to say that we want to create an object that's called our contract source code. That contract source code needs to specify the version that we're using. So in our case is Pragma Solidity 0.08. And because Solidity is actually a variation of JavaScript and one other language, I believe, we need to make sure that our notation includes semicolons at the end of all of our major lines here. Now, after we've specified our version here, we're going to lay out our contract, and ours is just going to be called contract, simple contract. Our simple contract is going to consist of some integers. In our case, we're going to use uint256, 256-bit algorithm that we were working with earlier. We're going to continue on with that. And that integer will be public and will be known as my number. Now, what we're going to do is create a function inside of this contract that will be called set the number, and setting the number will take in that integer and a number. And once we set that number, we're going to have an object in there that's called my number, which will be equal to the number that we set in the set number function. And that's where we're going to end it for right now. We're going to keep this very simple for this first example. Now, once we've laid out this source code for our contract, we basically need to set up some input data or some metadata that goes along with all of our Solidity smart contracts. So we're going to create a new object that's called input data. And in this input data, we need to specify which language we're using. So in our case, Solidity. We need to specify the sources for our data. And in our case, we're going to have a file that we're going to call simplecontract.sol.solidity, and that is based off of our contract source code up here. So within the simplecontract.sol file, we're going to specify the content to be equal to the contract source code. Now, outside of that basic input structure, we also need to put in some settings. Settings are simply just the output selection. So we're going to ask for the metadata, the EVM bitcode, and the EVM bitcode source map. And then we can close up all of that input data here and call those two objects done. After we've created our input data and our contract source code, we can actually go ahead and compile our data. So we're going to create a new object that's called compiled sol or compiled solidity, which will be equal to the compile standard. And that compiled standard needs our input data. So it needs this information here. Once we've standardized and created our input and compiled our input data, we're going to print out that input data, and then we're going to create our initial contract interface between our environment and between Ethereum, the Ethereum network. So we're going to call them the compiled sol, and we are going to subset and slice in to the compiled sol and access the contracts in there, and we're going to tell it what the name of the file was. So ours was simplecontract.sol, and then we're going to tell it the name of the object within our simplecontract.sol file, which in our case the contract was named simple contract, and all of that will be fed to an object that's called contract interface. And when you actually run this code, this is the output you get. A lot of this doesn't mean much to us, but you'll see that it's telling us that we've got our contracts. It's telling us that within the contracts object, it's accessing the simplecontract.sol, and that then it's got all of the bit code that goes along with that contract interface that we've just created. So at this point, we've compiled our Solidity code and we've generated the contract interface. Now we're actually at the point where we can deploy this contract to the Ethereum network, and we're going to do that using the Web3 library. So the Web3 library holds all of the HTTP protocols and other networking functions that we may need to interact with the Ethereum network. So we're going to come in and install the Web3 library. After we've installed the Web3 library, we're going to come in and say from Web3 import Web3 as well as HTTP provider. Then we're going to come in and name a new object called W3 or Web3, which will be equal to the Web3 function and the HTTP provider. In our case, we're using a local host. We'll then name the Ethereum account and access that account. We're then going to name our simple contract object, and we are going to tell it how it's interacting with that object. So we're going to say that we want to take the W3 object.eth.contract. The ABI is basically like an API. So ABI stands for Application Binary Interface. And we're going to take the ABI of our contract interface, that object we just created, and call on the ABI specifically. And we're going to say that the bit code or the byte code of our ABI and of our contract interface is equal to the bin. And the bin is essentially the active folder of that environment. So we're using all of this code here to basically create the actual object for that simple contract. And from that simple contract, we're going to create a constructor, and that constructor is going to call on a transact function. This transact basically stands for transaction. So it's making contact with the network and then waiting for information about receipt of the contract or of the data that we just sent. And we're going to save all that as the TX hash. Then we're going to take the TX hash and we are going to pass it to the w3.eth.wait for transaction receipt. So we basically have sent the information in the TX hash object, and then we're going to create another object called TX receipt, which is where we're going to take the TX hash, pass it to the wait for receipt function, and then save that receipt as our information here. Now, once we've received our receipt, we're going to create a final object that's called simple contract. Simple contract will take in the W3 ETH contract and pass it the address, which will be txreceipt.contract address. And then it's going to tell it how we want to interact with that data, which was using our ABI, our application binary interface. And that binary interface is going to come from the contract interface, which has the ABI and the byte code built into it, or bit code built into it. After that, we're just simply going to ask for a printout. So at this point, we have deployed our contract onto the Ethereum network, and our initial value for the my_number variable is just 0. We haven't actually set the value. So after that, we can come in here and say on that simple contract object, that object that we've interacted with right here, I want to take that object, I want to use our functions built into the contract, and I want to use the set number function that we defined earlier to set the number of my contract to 42. And then I want to call on the transact function to create that transaction and wait for a receipt. After we've waited for our receipt, we can print that number out and show that we've actually successfully deployed and altered that number on the Ethereum network. And if you wanted to build a blockchain network or a blockchain app from the ground up, we've got some basic steps that we can go over here really quick. So to deploy a decentralized blockchain app, you have to have basically 5 or 6 different parts figured out. The first of which is your smart contract. So you need to know how to program in Solidity and how to design these smart contracts for your Ethereum network or your Bitcoin network, whatever network you're working on. And you also need to be able to define functions that allow you to create and transfer data through that network. So in this example, I mentioned NFTs, non-fungible tokens, which are commonly used for artwork or just storage of secure information, and that would be what is passed on that smart contract. Besides the smart contract, you also need to understand token standardization. To be honest with you, I don't 100% understand all of these protocols. I haven't read through them all myself, but for each smart contract, you want to lay out a set of protocols that should be used with that contract. So some examples from the Ethereum network are ERC 721 and ERC 1155. And these basically just create standards for the workflow of something like an NFT that is being sold or or move through a smart contract, and then based on these protocols, they can be created, transferred, and owned by individuals that are on that decentralized network. Once you've got your smart contracts and your tokens figured out, you need to pick a hosting platform. So some common platforms that people deploy applications are Remix, Truffle, and Ganache. I've heard of Remix before. I've never personally used Truffle or Ganache. And then just because you actually have your contract deployed and you're hosting it somewhere doesn't mean that someone like me or you can see it out in the public. You've got to be able to build and create the interfaces to interact with those smart contracts and those NFTs or whatever you're using. You can integrate those with the network and everyday people can see them. And then of course you need to be able to test them and to launch them. So if we were going to lay out a basic structure of how you can build a decentralized application, I would say that you need to be able to handle these 6 or 7 steps. Now, Python has kind of become the Swiss Army knife of programming. It can be used for almost any application in programming. The big issue is its speed. Now, one of the benefits of working with a established network like Ethereum is they have their own protocols built, they've got their own programming language, and you saw we can integrate their programming language with Python fairly easy. So in the future, I suspect that Python will play some role in development of blockchain technology. But overall, I think there are a couple areas of blockchain technology that will really explode and take hold in the next couple of years. One of them, of course, is decentralized finance. As I talked about in the first part of this series, banks like Bank of America and other large financial institutions have been preparing for the advent and the adoption of these blockchain technologies for probably 5 to 10 years. So they're ready for it. We're the ones that are going to have to adjust to them, not the other way around. And so finance will be this really interesting sector where the technology is going to grow so fast and adoption will kind of come behind it. Now, one of the other areas that has already been growing exponentially since about 2020, maybe 2021, are NFTs, non-fungible tokens, and digital art. And when people think of NFTs, they commonly think of digital art, but NFTs are much more than that. It's essentially a QR code with a unique signature that guarantees your secured ownership of. NFTs may be used for the deed to your house. NFTs may be used for your health insurance. NFTs may be used to secure a loan. There are many, many different ways that an NFT can be used. And simply by having that accessible on your smartphone, you then can secure your asset, or you can prove your ownership of your asset. And there are other sectors that I expect major developments in, one of them being supply chain management. Since 2020, we have had supply chain issues across the world, with ships sitting at sea waiting to be unloaded, for sometimes months at a time. And moving supply chain management onto a blockchain and decentralizing it and enabling speed and efficiency through smart contracts is a major sector of growth over the next 2 to 5 years. With that also will be healthcare. So a lot of the times people have their healthcare records either stored on paper, and they bring their doctor, if they go to a new doctor, they bring their doctor a copy of their health records on paper. In many cases now they're emailed back and forth. That's still not necessarily secure. Email gets hacked all the time. So I assume we will see major development in the healthcare sector with blockchain specifically for things like health insurance, secure medical records, getting prescriptions that cannot be forged, analytics, as far as medicines go, as well as incorporating machine learning or AI for predictive analytics of x-rays or CAT scans, personalized treatment plans. So instead of one-size-fit-all solutions, we can start to customize a little more because everyone's got a unique signature on the network with unique data points. So these are some of the areas that I really expect to explode in the next couple of years, or to grow rapidly in the next couple of years. And I can't necessarily say that we 100% will adopt every solution that will take hold, but I do expect there to be rapid advancement in these fields globally. Now, with any kind of technological revolution, there are always challenges. So some of the major challenges when it comes to blockchain are, of course, scalability. Right now, we have all of the data in the world on a web framework or a network protocol framework we call Web 2.0. We need to convert all of that data in the world from Web 2.0 to Web 3.0, and then deploy all of that as decentralized applications or private networks that then integrate into decentralized networks on a blockchain in the cloud. That is a gigantic issue to solve. One, we don't have enough servers. Two, we don't have enough blockchain developers to actually do the work to deploy them to the cloud. So scaling this is going to be a major problem. And I don't really see any advancement in the training of blockchain developers at this time. For instance, Microsoft has cut 10,000 jobs this year. Google has cut, I think, 15,000 jobs this year. So these big tech companies are working backwards. They're cutting jobs to save money right now because of the economy. And so at that same time, that means we're actually slowing the development of technologies like blockchain. So I'm not really sure what happens in that sense, but either way, people will continue to try to develop blockchain technologies, and we're going to have to figure out how to handle all of the back-end networking and functionality to scale these applications and develop this new internet that we are working on. With that, we also have regulatory issues. So you guys may have heard in the news recently, people are worried about AI becoming too powerful and the fact that we need to regulate it. At this point, blockchain is growing rapidly and becoming more widely adopted. And at this point in time, we actually have limited regulations and laws around blockchain technologies. So with anything, governments will step in and try to regulate these processes and create some kind of standardized process. That has started, but it is not moving quickly. So that's a whole nother problem that we have to try to solve. And then, of course, innovation. And innovation is a good challenge to have. In many cases, when we have technological revolutions, we actually can't even imagine the innovation that comes out of them. In advance, it's hard to imagine ideas like Apple or like the laptop or cell phones. You don't think of those things in advance, or at least 99% of the population doesn't. So one of the exciting things about blockchain is the innovation and the creativity. It'll be really interesting to watch how the world changes as these new technologies are developed. So with that, we are done with our blockchain series. I hope you found this information really insightful and helpful. I hope you have a wonderful day, an even better rest of your week, and I'll see you next time.